we have our last speaker. So let me introduce Mattia, who Mattia from Stellantis. Mattia graduated in environmental chemistry with honors, with a PhD project in chemical and material science. Mattia has been working at Centro Ricerche Fiat, CRF, since 2017. He covered different positions, focusing on different technical aspects, topics related to the automotive field, which may involve catalysts, batteries, product development. He had the chance to work with many different topics, which are concerning the characterization, validation of materials for R&D and routine activities. And he's also involved in submitting and following up on several European funded projects. Currently, Mattia is covering a global position as technical reference in the Stellantis group, specifically on materials for lithium-ion batteries, with direct involvement in discussions related to the active materials and associated raw materials, managing also a dedicated laboratory, which is dedicated to the validation and evaluation of these types of materials. Mattia, will leave the floor to you.
Thanks. I shared my screen.
Yes, thank you.
Okay.
I do see it. Yeah.
Great. Okay. Okay. Can you see the screen in full presentation mode?
Yes, I do see your taskbar below.
Oh, okay.
I think I see a PDF actually.
Now,
yeah, now it's okay.
Okay. Yeah. No, it's because I'm working on two screens. So I will skip the first slide because Daniele already introduced me. So I will start with very brief introduction of what Stellantis is, because Stellantis is a brand new, or maybe not very brand new, automotive group born in 2021 from the merging of PSA and FCA Group, becoming the fourth world largest automotive group and creating a strong global and worldwide organization. Within Stellantis, we have RF and the department that I'm part of, which is a R&D department focused on the development and transfer of innovative solution on all the aspects of the vehicle, with the target to improve the competitiveness of Stellantis product. And it's also the representative of Stellantis in European and national collaborative research programs. In this presentation, I will try to give a overview on the relationship between solid-state batteries and automotive world. In the moment, the current generation of cells installed on the vehicle is it's quite advanced, because we are around generation 3A with target to achieve generation 3B very soon. But clearly, the target is to go after and go in the post-Lion, in the post-lithium-ion world. So in generation 4 and in the future generation 5. What is the current situation? Despite a growing demand of lithium-ion batteries worldwide, drive also by the mobility, there are still several open issues. the energy density limitation, because the current technologies are approaching the theoretical limits, so we need to improve the capacity of the material applied. Safety concern related to the risk of thermal runaway, fire, explosion, the electrolyte, in particular due to the electrolyte flammability and dendrite formation. The cost and the resources constraint, for example, depending on the dependence on critical raw material, the price volatility of this kind of raw material, and the supply chain risks. The cycle life and degradation, so the quite fast capacity fade and the limited high temperature and high rate performance capability. In this context, clearly, solid-state battery represent a sort of holy grail for the automotive application, because they can lead high energy density, increasing the driving range, high power density in order to improving the fast charge, long cycle life in order to have a battery that can cover the entire vehicle lifetime, wide operating temperature condition, enhanced safety, reducing the fire with a reduced fire risk. But also but also the scalability and the low cost production, and also thanks to the higher energy density, a reduction of the weight and of the volume of the cell, with a lightweight and more compact design of the battery pack, with more space and better efficiency from the space point of view. All the claims are very nice, but they have to face with the reality of the solid-state batteries. First of all, solid-state, it's a very big word. The reality that many of these kind of technologies have still some liquid or gel components, so they are more solid or hybrid systems. The energy density clearly can be improved a lot, in particular with the application of lithium metal on anode side, but it is not guaranteed. And in general, the improvement is more on gravimetric energy side, while on volumetric energy density side, this improvement is not realized yet. In terms of fast charging capability, we have many solid electrolyte exhibit lower rate capability compared to the liquid electrolyte, and the interface limitation limits the transport and create constraint for the higher C rate, in particular and at room temperature. Another important aspect is that this transport is also very sensitive to the solid electrolyte material applied and on the cell construction, on the cell construction. In terms of driving range, the vehicle driving range doesn't depend only on the energy density of the cell alone, but it depends on the total system mass and efficiency. So even with a substantial improvement from this point of view at cell level, the real impact at the vehicle level is from the practical point of view quite reduced. In terms of safety, we have to bear in mind that most of the solid electrolyte are inorganic and not flammable, reducing the fire risk. However, the electrical short, lithium metal reactivity, mechanical failure can still lead to the thermal events under specific conditions. Furthermore, trace of moisture can, during manufacturing, but also during the operativity, can lead to gas formation or reaction in some system, in particular on sulfide-based electrolyte and in presence of metallic lithium. In terms of manufacturing, many of the current solid-state batteries electrolyte technologies contain rare materials and must be produced using expensive and not scalable techniques. So the manufacturing is still not very cost effective. Also because it consider also the handling of very delicate material as lithium metal or sulfide base, which require special environment and also for example, for the ceramic, the solid-state electrolyte needs to have 100% defect-free product in order to achieve interesting performance. Another important trend from the integration at automotive scale of solid-state batteries is related to the dimension variation of the cell, because we have the swelling of the cell derived, which happen in the first step of cell life due to the undesired side reaction happen in the very first cycle. But we have also the breathing, which happen due to the stripping deposition of the lithium during the charge and discharge. This breathing and swelling can affect and can change and can create a shrink of the cell dimension around 20-30% of the total volume. This behavior reach a plateau after some cycling, but this dimensional change create mechanical complexities during the integration at pack level, and can negatively affect the volumetric energy density at module and pack level. Another very important aspect is the pressure, because in order to improve the interpressure resistance and the mechanical contact between the cell component, a compression force is necessary to improve all this performance. So the integration of properly designed pressure system is mandatory to extract the full potential from this kind of cells, but clearly it increases the complexity of the battery system. So and this lead additional weight and additional volume, which affect the real gain in terms of energy density at pack level. Another important aspect is the raw materials involved, because the solid-state batteries can potentially expand the critical raw material footprint of the product, not only related to the increasing lithium intensity required by the application of lithium metal anode, introducing new supply chain risk that must be addressed during the manufacturing. And here in this table, you have some example of the element involved in a solid-state electrolyte. Looking to the general roadmap, every solid-state electrolyte has pros and cons, and in the short terms, the respective technical bottleneck still hindered the upscale of these technologies. The perspective for 2030 and after will be focused on the overcoming of this limitation in order to achieve a potential upscaling for these technologies. Looking into the possible usability scenario, polymer solid-state batteries are already in the market also on a quite large scale. They are still limited in terms of operating temperature, and it is an important drawback. But several strategies are already in place, and this technology, from the automotive point of view, is already applied on electric buses, but also on some electric vehicle application. Sulfide-based is probably the most interesting chemistry for the mobility, due to the high energy density and also to the good conductivity. But it's still in R&D scale or pilot scale. It depends on the different technology, and the price is still high and not competitive with lithium-ion. So probably the first usability scenario will be the mobility, but these bottlenecks have to be overcome. Similar situation for oxide solid-state batteries, which, thanks to the higher stability of material, could be also applied on heavy-duty machinery and together with the electric vehicle. a quick overview of the market. In the slide, you have a summary of the main industry players all around the globe that are working on solid-state batteries. In the slide, you have a distribution of these main players in the development step for the application of a new technology into a real automotive application. As you can see, many players are still in development stage. Normally, the development stage it's a long process. It can take between 8 and 10 years just to get a sample A for the automotive application, and after that, another 4 to 8 years are needed to pass from A to B to C to D sample and achieve a real product launch and the real commercialization of the technology. And we are also to bear in mind that during this development phase, we are spending the developer are spending money. So because build manufacturing plant takes several years and commission from capital expenditure. And solid-state battery require new manufacturing machines and product line which require high precision and high automation and to be cost competitive. In parallel, also the supply chain are sometimes immature and need to be improved. So Gigafactory burn money in the first stage, also because the qualification and the approval from a automotive end user could take year. Why it takes year? Because it's a loop process. Clearly, the technology producer developed the cell, optimizing chemistry, focusing on energy density, the electrode formulation, performing also internal validation, but this validation has more focus on performance, manufacturability, and cost optimization. When a technology is submitted to a validator, like an automotive validator, like CRF, the automotive validator tests this kind of technology in a more realistic condition with power profile deriving from the real usability scenario, testing, for example, fast charge, long-term cycling, calendar aging in different conditions, and also trying to get the compliancy to the international reference norm, for example, from the safety point of view. The feedback from this performance evaluation on validator side could restart sometimes the cell development and the design optimization made by the technology producer, and this can increase the time needed to achieve a commercial product. For all the reasons that I described before, in general, the forecast of solid-state penetration by the battery industry player is quite limited. It's very limited for 2030, but even in 2035, the forecast by the battery maker and battery player is still limited around 10%, around 10%. Just to make a quick overview on the main players for the solid-state batteries for mobility application. Blue Solution is working on polymer solid-state electrolyte with lithium metal anode. They have already in big scale production a generation based on LFP. They are working on a new generation based on high voltage cathodes for the next feature, and they are strong partners of BMW and also Stellantis. QuantumScape, they are focused on anode-free solid-state lithium metal battery, which use a hybrid ceramic solid electrolyte. They are they are receiving a lot of investment from Volkswagen, but the cell production is still at pre-pilot stage. Solid Power, they develop a sulfate-based electrolyte, and together with a battery maker that we through JV, they are also developing cells based on this sulfate-based electrolyte with high silicon anode and lithium metal anodes. And this development is partnered with BMW and Ford. Prologium is building a ceramic-based NMC solid-state battery. In this moment, with silicon oxide graphite composite and lithium metal is planned for the new generation. They licensed this technology to Mercedes-Benz and NIO, and they also announced a plan to open a plant in France for the automotive solid-state battery production. Factorial, the technology of Factorial is based on a proprietary polymer-based electrolyte used to manufacture semi-solid state battery with high nickel NMC and lithium metal anode. They achieve the production of 100 ampere-hour full-scale cell, and this cell is provided to Stellantis for an automotive qualification. The large-scale manufacturing is already in place, and they expect to start the commercialization in 2028-2030. Ganfeng, it's a company leader in the lithium production, hydroxide, and lithium metal. But they also launched a solid-state lithium battery as an R&D program. They already developed 2 generations of this technology, both based on NMC cathode with different anode, but both with oxide-based electrolyte. These semi-solid cells are in production and are implemented in some vehicle demonstrator through a collaboration with Dongfeng. Wilion is developing a similar technology, so high nickel MC cathode with silicon anode and oxide-based semi-solid electrolyte. This technology is also in production and is applied on NIO vehicle application, but we will talk again about this application after. Samsung is well known. It's one of the most important battery maker worldwide, and it's already supplier of many important vehicle OEMs. They have a program based on anode-free solution with a sulfide-based solid electrolyte. The scale-up is ongoing, and the target is to reach the mass production in 2027. Toyota, it's the leader in the solid-state batteries development for electric vehicle. They focus their attention on sulfide-based solid-state batteries, and they make several announcements. And now the plan is to start a limited production of solid-state batteries equipped with the EV around 2027-2028, with a partnership with Panasonic and Idemitsu. About NIO and Wilion. NIO in 2021 announced the production of this very powerful battery pack with a very long range, thanks to the application of the semi-solid state batteries developed by Wilion. This announcement submit to multiple delays, and in the end becomes real only in June 2024. But only for rent application through NIO swap station only in China. After less than 1 year, the production of this technology was paused due to the lack of interest and the high price of this solution. More in general, looking to the well-known battery car maker, the development of solid-state batteries started more than 15, sometimes 20 years ago. But after that, there were several claims, several announced, but also several delay in this announcement. For example, for the production date for the Toyota solution was postponed several times in the last year. Also for the technology developed by Volkswagen and QuantumScape, in 2025 QuantumScape achieved the B sample and C sample will be follow, but with an undisclosed time frame. Same situation for the cooperation between Solid Power, Ford, and BMW. They achieve a sample A sent to the OEM in 2024, but the validation is still ongoing. And in general, the initial volume expected will be very low, and the ramp up will cover other several years to be improved. Looking to what Stellantis have in place from this point of view, there are 3 main programs related to solid-state batteries. The program with Blue Solution focus on high power application. The partnership with Factorial focus on high energy pack based on lithium metal and polymer electrolyte, and AC for high energy and fast charge battery pack. And about Factorial cooperation, recently Stellantis shared publicly the announce of the integration of a full solid-state battery pack on a vehicle for the launching of road test for real drive validation activity on this disruptive technology. So to wrap up this topic, solid-state battery is indeed a game-changing technology able to overcome some of the most critical aspects of the state-of-the-art lithium-ion chemistries for the automotive application. Vehicle OEMs are investing important resources in this field, and some very interesting applications have been applied and demonstrated. The problem is that the upscale and the diffusion of this technology is anyways hindered by important technical bottlenecks which affect from the cell manufacturing point of view to the vehicle integration to the performance of this technology. But we have always to bear in mind that electric mobility is not the only target market for solid-state batteries, but there are also other application where the technology is already a solid reality or the maturation level is still in advanced stages. So thanks all for the attention, and if you have any question.
Thank you, Mattia. I have a question which is also partially related to the last message from Stefan. It's specifically on the competition between solid-state batteries and high performance or conventional lithium-ion batteries, which from another point of view, the outstanding performance which the recent lithium-ion batteries are showing. Do you see this diffusion of lithium-ion batteries in the automotive market as something realistic, and will they compete on the same type of products, or we can foresee, for example, an application in different products, such as could be high-end products or buses, such as in the case of Blue Solution? So we can imagine 2 different so like a large scale application of lithium-ion batteries in most of the vehicles, and some niche applications where solid-state batteries could be advantageous, for example.
I mean, it's difficult to give a clear answer. I agree. I agree with the last slide presented by Stefan, because in parallel to the development of solid-state batteries, the lithium-ion world is not stay still, is not stop any development because the future is solid state, but also lithium ion, liquid electrolyte lithium ion technologies are improved further. And for some type of chemistry, the improvement was the improvements were and are quite astonishing. In particular, for example, for in the LFP the LFP based cells are making very interesting technology jump, and they are becoming very interesting also for application that 4 years ago was only for NMC. The factors that can affect this selection are many. The cost is clearly one of the main drivers. So in this moment, solid state batteries are for the visibility that I have for the automotive field has still too many bottlenecks. There is not yet a real game changer technology that can overcome the bigger problem that this technology has in order to transform this technology in a mass production, in a mass application technology. So speaking about what will be the future of solid state battery in automotive field, probably the next future will be application for niche field. So very powerful application. So race car or a high level car in terms of price, in terms of price, and in terms of performance. So for a limited field. There are, as I said before, there are also other fields where solid state probably are closer, sometimes are also already a reality, but sometimes are also closer to a more spread applicability. For example, drone fields where the battery required is smaller. So from the production point of view, the upscale is less important. So there are many different factors that could affect this trend.
Thank you, Mattia.